Jai Hind to all. Today we will be studying chapter Light, which is chapter 10, and we will be studying the concept of reflection and refraction of light. Now previously we have studied about the chapter Light and we know about certain characteristics of light. For example, light is a form of energy which helps us to see objects. Then whenever light falls on an object, it reflects the light, and when the reflected light reaches our eyes, then we see the objects, which is basically the concept of reflection of light. Light travels in a straight line, also known as the rectilinear propagation of light. And there are certain phenomena which are related to light. Some of them we are going to study in this chapter. For example, formation of images by mirrors and lenses, bending of light by a medium, twinkling of stars, formation of rainbow, all of it which we are going to study. So to start with, we are going to study the concept of a reflection of light. Now, whenever light falls on a shiny or a polished surface, it changes its direction, and this is known as the reflection of light. Now, this reflection of light follows certain laws which are known as the laws of reflection. Now, before we start with the laws of reflection, I want you to look at the slide and look at the diagram, the first diagram. Now, here light is falling on a plane mirror, as we all can see. The light which is falling on the plane mirror is the incident ray. And when it hits the plane mirror, it's going to change its direction, and that is known as the reflected ray. Now, in between we have drawn a normal. What is a normal? Normal is actually a line, a ray that we draw that is perpendicular to the surface. Now, how is normal helpful to us? With the help of normal, we can actually find out the angle of incidence and angle of reflection. So now we have all the three with us. We have the angle, the ray of incidence, then ray of reflection, and then we have the normal. So the angle between the normal and the incident ray is known as the angle of incidence, and the angle between the normal and the reflected ray is the angle of reflection. So the first law which we have for the reflection of light is that the angle of incidence is equal to the angle of reflection. That is, angle I is equal to angle R. The second law that we have is that all the three rays, that is the incident ray, the reflected ray and the normal, are going to lie on the same plane. Now, the first kind of mirror that we are going to study is the plane mirror. Now, there are certain characteristics of the image which are formed by a plane mirror, and all of them are listed here. The first characteristic is that the image is erect. Second, the image is same size as the size of the object. The image is at the same distance from the mirror as the object is in front of it. Image is virtual, so we generally say that the image is virtual and erect. And then the image is laterally inverted. Now, we can understand all these characteristics with the help of the diagrams which are shown in the slide. Now, moving on to the first point, that the image is virtual and erect. Now, any image which cannot be obtained on a screen is a virtual image, and any image which can be obtained on a screen is a real image. A virtual image is always erect and a real image is always inverted. So, virtual and erect is the nature of the image that is formed by a plane mirror. The second point is that it is of the same size. So, when you look at the second diagram here, you can see that the object, which is a man who is standing in front of the mirror, let's say he is standing at a distance of 2 centimeters from the mirror. Then the image will be formed at 2 centimeters behind the mirror. And the image is of the same size as the object. So whenever you see yourself in a plane mirror, you might have noticed that the image formed is of the same size. And then the image is laterally inverted, which is the third diagram which you can see, that the left appears right and the right appears left. Now, if the reflecting surface of a mirror is curved, then those are known as the spherical mirrors. And we can classify spherical mirrors into two types: concave mirror and convex mirror. Now, the first kind of mirror that we are going to study, concave mirror, is also known as a converging mirror. Now, it's a spherical mirror whose reflecting surface is curved inwards. So, what is a spherical mirror? Whose reflecting surface is curved. If the reflecting surface is curved inwards, it's a concave mirror, right? And the first diagram which you can see is of a concave mirror, which is also known as converging mirror, and you can clearly see why. So the rays which are parallel to each other, whenever they strike this mirror, they are all going to meet at a point which is known as a focus. So this mirror is actually converging all the light rays to a point which is known as a focus, right? And then the second type of a spherical mirror whose reflecting surface is bent outwards or curved outwards is known as a convex mirror. Now convex mirror is also known as a diverging mirror. So it's going to diverge all the parallel rays which are falling onto its reflecting surface, right? So this is the second diagram. So we have a virtual focus here. Now this is the basics of a mirror, that for a mirror we have one side as a polished side which is actually painted silver, coated silver, and then for protection we paint it. And then the other side is the reflecting side, right? So these are the certain basics and the shapes of a concave and a convex mirror. Now whenever in the later part of the chapter we will be studying about the ray diagrams or the image formation by concave and convex mirror. So to study those diagrams, it's very important to understand the terms which are related to the mirrors. Now the first term that we are going to study is the center of curvature, which is usually represented by C. Now center of curvature is the center of a sphere of which the mirror is a part. Then the other one is the radius of curvature, the second point. It's the radius of the sphere of which the mirror is a part. Pole. Pole is the center of the spherical mirror. It is center of the reflecting surface of a spherical mirror. Then we have principal axis. Principal axis is a straight line which is passing through the curvature and the pole. Then we have principal focus, as we have studied earlier. In concave mirror, the rays of light which are parallel to the principal axis after reflection meet at a point which is known as a focus. And in a convex mirror, the rays of light which are parallel to the principal axis after reflection gets diverged and they appear to come from a point which is known as a focus. And then we have focal length. Now focal length is the distance between the pole and the principal axis, right? And in a spherical mirror, you need to remember this formula, that the radius of curvature is twice of the focal length. Now there is another term which is the aperture. Now the diameter of the reflecting surface of the spherical mirror is called its aperture. Now in this slide you can see all the terms that we have studied. You can see the pole, which is the center. Then there is the center of curvature. Now we can see that through a dotted line, we see that the mirror is a part of a sphere and the center of that sphere is the center of curvature. But the center of the reflecting surface of the mirror is a pole, right? And we can see here the radius of curvature, mm dash represents the aperture. Now again, these are all the terms being explained here, so you can go through it. Now reflection by spherical mirrors, in order to study the ray diagrams, we need to know the certain laws from the ray diagrams, certain rules. So there are certain rules which we can see both of concave and convex mirror. Let's go through the first rule. The first rule says that in a concave mirror, a ray that is going parallel to the principal axis after reflection is going to pass through a focus, right? And what happens in case of a convex mirror? A ray of light that is parallel to the principal axis after reflection appears to diverge from the focus. So that is the first rule. Second rule, in a concave mirror, a ray of light that is passing through the focus after reflection will go parallel to the principal axis. Now if you carefully look at this rule, you're going to see that it's actually the reverse of the first one. So a ray that is passing through the focus is going to go parallel to the principal axis for a concave mirror. And for a convex mirror, a ray of light that is directed towards the focus after reflection would go parallel to the principal axis. And the third and the last law, in a concave mirror, a ray of light that is passing through the center of curvature after reflection is reflected back along the same path, right? So this is the same law for both concave and convex mirror. And then we have, in a concave or a convex mirror, a ray of light that is directed obliquely at the pole is reflected obliquely, making equal angles with the principal axis, which is shown through the diagram. Now this slide actually shows the image which are formed by a concave mirror. Now in ray diagrams we actually study that if you are changing the position of the object, how is the nature and the position of the image is changing. That is the importance of a ray diagram. And why do we study the rules? Because to make the ray diagrams, it's important to study the rules. If you know the rules, you will be able to make the ray diagrams very, very easily. So let's go through all the image formation by a concave mirror one by one. So the first one, we can see that AB actually represents the object and the object is at infinity. So there is an object at infinity. A practical example, let's say you have a concave mirror and there are rays coming from the sun. The sun is located at infinity, right? So whenever the rays from the object which is at infinity strike the mirror, they all are the parallel rays. They are going to hit the reflecting surface of a concave mirror. And as per the first law that we have studied, rays which are parallel to the principal axis are going to meet at the focus. So that is what is there in the first ray diagram. The rays which are parallel coming from the object at infinity are going to reflect back and meet at a point which is known as the focus. Now what we have done, we have shifted the object closer to the mirror. So now we have the object closer, it's beyond C now. It's not at infinity. Now we have shifted it closer to the mirror and now our object is beyond C. Now in the first ray diagram, when the object is at infinity, the image you can see is formed at the focus. We can look at the size of the image, it is point size, and the nature of the image is real, right? Because the rays are actually meeting. So it's a real image. So real and inverted is going to be the nature of the image. Now for every ray diagram that you're going to study, you need to know these 4 points. What is the object position? What is the image position? What is the size of the image? And what is the nature of the image? Moving on to the second ray diagram, the object is beyond C. Now when the object is beyond C, as you can see, the image is formed between the focus and the center of curvature. Now here, the size of the image is smaller than the size of the object and the image formed is real and inverted. Now how can we say that the image is real and inverted? Because it is formed below the principal axis. Moving on to the third ray diagram, the object is at C. So now we have shifted the object closer to the mirror and now our object is at the center of curvature. So when we apply the laws, so what laws have we applied in the third ray diagram? A ray that is going parallel to the principal axis is passing through the focus and a ray that is passing through the focus is going parallel to the principal axis. Now here you can see that the image is formed at C. So the object is at center of curvature and the image is also formed at the center of curvature. What is the size of the image? The image is of the same size as the object and the image is real and inverted. Why real and inverted? Because as we can see, the image is formed below the principal axis. So it's inverted and real. Moving on to the next ray diagram, the fourth one, which is the D part here. We have shifted the object further closer to the mirror. So now the object is between C and F, right? So now as per the laws and as per the rules that we have studied earlier, we can see that the image is formed behind the center of curvature. And if you carefully look at the size of the image, it is bigger than the size of the object, right? So that is why the size of the image is enlarged and it is real and inverted. For the next ray diagram, we have shifted the object further close to the mirror. Now our object is at the focus. So the image is formed at infinity and it is highly enlarged in size and the nature is again real and inverted. And for the last ray diagram, here the nature of the image changes. Now when the object is very close to the mirror, that is, you can see the position of the object, it is between F and P. So when the object is very close to the mirror, the image is formed behind the mirror. That means that the nature of the image which is formed is virtual and erect. How can you identify that the image is virtual and erect? See if the image is formed below the principal axis or if the image is formed above the principal axis. If you carefully look at this ray diagram, the image is formed above the principal axis. So it is virtual and erect. Size, as we can see, is enlarged and the image is behind the mirror. So this is the only case in a concave mirror where the image formed is virtual, erect and enlarged. For all the 5 cases, you can see here that the image formed is real and inverted. Now this is the table which is actually showing the object position, image position, size of the image and nature of the image, which we have already discussed. Now this was the image formation by a concave mirror. We now move on to a convex mirror. So these are the two ray diagrams which we are going to study for a convex mirror. First ray diagram, as we can see, what is the position of the object? The object is at infinity. Now again, practically you can imagine that, let's say this object is sun and sun is situated at infinity. There are parallel rays falling from the sun onto the reflecting surface of a convex mirror. What is the convex mirror going to do? It acts as a diverging mirror, so it's going to diverge all the rays, right? But these rays are going to meet virtually at a point which is known as a focus. So this is the first ray diagram where the object is at infinity, image is formed at the focus and the focus is situated behind the mirror. And what is the size of the image? The size of the image is highly diminished, its point size, and the nature of the image is virtual and erect. The second one is the position of the object is between infinity and the pole. So on applying the rules which we have previously studied, we see that the position of the image is between P and F, which is behind the mirror. Image size is smaller than the size of the object. So that is why we have written that the size of the image is diminished. And since the image is formed above the principal axis, it is virtual and erect. So these are the image formations by a convex mirror. Now what are the practical uses of concave and convex mirrors in our day-to-day lives? First, let's look at the uses of concave mirror. Now concave mirrors are used in the torches. So the reflector of the torches, these are concave in shape. And searchlights, headlights, they also use concave mirrors. After that, they are also used as shaving mirrors to see larger image of the face. Then they are used by dentists to see larger images of the teeth. And large concave mirrors are used to concentrate sunlight to produce heat in the solar furnaces, because we have studied there these are converging mirrors. So these are some day-to-day uses of concave mirrors. Moving on to the uses of convex mirrors. The major use of convex mirrors that are its use as a rear view mirror in the vehicles. And convex mirrors give erect, diminished images of objects, so they also have a wider field of view than plane mirrors. Now, that is the sole reason why we use convex mirrors as a rear view mirrors. So it actually forms a smaller image, so it covers a larger area. So it gives a wider field of view to us. Now you must have observed these kind of mirrors also in the supermarkets. Now these are also convex mirrors. Now these are also used for security or surveillance purposes in supermarkets. You might have also noticed these kind of mirrors at metro stations, in the parking areas. All these kind of mirrors are convex mirrors. Because they form small images, virtual images of the object, they cover a large area. They give a wider field of view, which is the main reason why these are used for security and surveillance. Now there are certain sign conventions which we are going to follow for the spherical mirrors. Whenever we take the object towards the object or any distance which is towards the left, we take it as negative. All the distances that we take towards the right side of the mirror are taken as positive. So if we go through the points here, the object is always placed on the left of the mirror and light from the object falls from left to right, right? And all the distances which are parallel to the principal axis are measured from the pole. All the distances which are measured to the right are taken as positive. All the distances measured to the left of the pole are taken as negative. Whatever are the heights that we measure above the principal axis are taken as positive. Heights which are taken below the principal axis or downwards the principal axis are taken as negative. Now we will be studying about one formula which is known as a mirror formula. This is the mirror formula which is given by 1 upon V plus 1 upon U equal to 1 upon F. Let's see what all these terms mean. Now V is actually the distance of the image from the mirror. U is the distance of the object from the mirror. And F represents the focal length. So if you're taking the distances on the left side, you will be taking it as negative. If you're taking the distances on the right side, you will be taking it as positive, and these are the sign conventions which you are going to follow when you are solving the numericals. Now, this is a mirror formula, and after which we have also a formula for magnification. What does the magnification represent? Magnification for spherical mirrors is ratio of the height of the image to the height of the object. So this ratio, height of the image, height of the object, is actually defined as magnification, right? The magnification is also related to the object distance and the image distance. That means that for magnification we have two formulas. One is in terms of height, image distance divided by the object height, and then we can also represent it in forms of distances, which is minus v by u. So the first formula is height of the image divided by the height of the object, and the second formula is negative of image distance divided by the object distance. So these are the two formulas which are related to magnification.